This is problem 15 of the unit conversion worksheet on mastering physics fundamentals. The ideal gas law, PV equals nRT. P is the pressure, V is the volume, N is the number of moles, R is the gas constant, which depends on what system of units you're using, and T is the absolute temperature. The gas constant is usually given as 8.314 joule per mole per Kelvin. So the question is, how many moles of gas will occupy 2.5 liters of volume at 25 degrees Celsius and 1 atmosphere of pressure? And we're going to have to do a deep dive. We have to be careful because we have to pay attention to units here. So we're going to write out the equation with the value of the gas constant there. PV is equal to nRT. There's our R. The rest are variables. The gas constant is, of course, constant. The volume can be expressed as, let's look at the units here. Length cubed is volume, so cubic feet, cubic centimeters. The pressure is force per unit area, which is newtons per square meter, for example. Force per length squared. Area is length squared. If you multiply pressure times volume, what unit do you get? You have length cubed in the top, length squared in the bottom. That's force times length, and that's energy. That's an energy. So standard unit of force is a newton, standard unit of length is a meter, and that's a joule, and that's energy. But a joule is not an atmosphere liter. We are giving the volume in liters and the pressure in atmospheres. So you have to convert these. An atmosphere is 101,325 newtons per square meter. So it's 1 atmosphere. So the pressure is 101,325 newtons every square meter. Now we have to convert the units of volume. There's 1,000 liters in a cubic meter. So there's 0.0025 cubic meters in 2.5 liters. Those volumes are the same because we multiplied by 1. So now we can substitute these numbers into PV is equal to nRT just to see where we're at. We got to take inventory here. There's the pressure, which is 1 atmosphere, expressed in different units. There's 2.5 liters, expressed in different units. And there's the number of moles. There's the gas constant, and there's the absolute temperature. If we focus on the left-hand side only, these two terms, we can multiply them. And we get 253 joules, because a joule is a newton meter, and we have meters cubed in the top and meters squared in the bottom. So that's energy. Now we're going to substitute the 253 joules in here. So in here is our PV is equal to nRT equation. So we can cancel the joule units. There's one here and there's one there. So the left-hand side is just a pure number. We still have to deal with that temperature. Temperature must be in kelvins. It must be absolute temperature. The Kelvin degree is the same size as a Celsius degree, but the scale is shifted by 273. So the conversion is simply you add 273 to the Celsius temperature. So 25 degrees Celsius is 298 kelvins. So we can plug in 298 kelvins for the temperature, and we can multiply out that mess on the right-hand side. The kelvins cancel, and we have a couple of numbers there. So we have 253 is N times 2480, 1 over moles. We can solve for N. And the units are moles. And we can do the math. And it's 1/10 of a mole. So at 1 atmosphere of pressure and about room temperature, 1/10 of a mole of an ideal gas will occupy about 2.5 liters. So if you keep the units throughout, and you do all of those ugly algebraic manipulations, the units are right there at the end. We didn't have to wonder what N was. The moles are right there. And these types of problems are great practice for being meticulous and patient. It's very valuable to have a reputation for someone that doesn't screw up, someone that's careless, that's careful and reliable, and doesn't make careless mistakes. They will be going to you because you have the reputation for not screwing up. That's problem 15.